So now let's look at some examples from 4.1. Now that you've watched the video from the lecture on 4.1. So let's begin with a derivative of 3x squared. So we're looking for what is a function that has 3x squared as its derivative. So you may recall from our videos that we were using the power rule. For the derivative, the power rule says we bring down our exponent, so we multiply by our exponent and we decrease our exponent. But for our antiderivative, and we use this symbol for an antiderivative, instead of multiplying, we're going to divide, and instead of decreasing our exponent, we're going to increase our exponent. So after we increase our exponent, then we divide by whatever that exponent is. And then we add an arbitrary constant, and we'll talk about that in just a second. So for our example, the antiderivative of this, we would do x to the 1 greater power. So 1 more than 2 is 3. And then we would divide by that exponent plus c. Now the 3 that we had out front to begin with and the 3 on bottom, those cancel. So a function whose derivative is 3x squared is x to the 3rd plus c. And remember, the way we would check that is we would take the derivative. If we took the derivative of x cubed, we would bring the 3 down, x to the 1 less power. And the reason we have this arbitrary constant on the end is because if we take the derivative of any constant, we would get 0. So we could have a constant of just 0 there, so basically y equals x cubed, and that derivative would be 3x squared. Or if this was a 1, the derivative of that would be 0. If this was a 5, the derivative of that would be 0. So we have to put an arbitrary constant out there because we don't really know what that original function was. We know the variable part, but we don't know the constant part. Eventually, we may be given some additional information so that we can find out what that constant is. But this is referred to as a family of solutions. They all have the variable part in common, but they have the vertical translation plus c as a difference. So let's look at another example. I can go to the next page. Let's do this one. Let's find the antiderivative of 3 minus x. The dx on the end, it just lets us know what our variable is for our function. So if we have a constant, our rule for integrating a constant is that we pick up our variable. If we have more than one term, we integrate them separately. So we integrated the first term minus integrate the second term. So what is our power for the x? If that's a 1. So to integrate or to get the antiderivative of x, we increase the power by 1. So 1 more than 1 is 2 over that exponent plus c. So you can write it this way, or you can write it 3x. We can bring the 2 out front and call that 1/2 x squared plus c. So that's the equation that has a derivative of 3 minus x. And of course, that would be easy to check to see, is the derivative of this really 3 minus x? So let's do another one. Let's do this one. This one doesn't have exponents that are all integers. Copy it. So we have 3 different terms. So we're going to get the antiderivative of each term separately. So for the first term, we want to increase our power by 1. And let's just come over on the side and say, what is 1 more than 3/2? Well, we would need a common denominator of 2. So if we double the bottom, we would double the top. So 5/2 would be our new exponent. So if we add 1 and make that 5/2, then 5/2 is what we divide by. Now, just as with derivatives, if we have a coefficient, we leave the coefficient alone, and then we take the antiderivative of the variable part. So we do x to the 1 bigger power over that power, and then when we take the antiderivative of a constant, we pick up our variable. Since we're doing dx, our variable is x, so we pick up an x, so 4x, plus an arbitrary constant. Instead of dividing by a fraction, let's multiply by its reciprocal, and then we can call that x to the 5/2. Here, 2 goes into 6 3 times, leaving us 3x to the second, plus 4x plus c. And then, if you're unsure, take the derivative of this and see, when we take the derivative of this, does that give us x cubed? When we take the derivative of that, does that give us 6x, 4, and does that go away? And they will. One thing I'll mention real quickly, notice there's not a coefficient out here. If we bring this 5/2 out front to go with the coefficient we already have, the 2's cancel and the 5's cancels. So when we take the derivative as a check to see, is the function we got really a function whose derivative is this, then yeah, the 5/2 and the 2/5 are going to cancel. So in our derivative, we aren't going to have a coefficient. So as we go through these, sometimes we get into ones that have radicals or fractions. I may not do the exact same problem, but similar. So we have a power rule. We have a rule when we have separate terms. We have rules for constants and coefficients. But just like with derivatives, we don't have rules for radicals. So we rewrite the radicals as x to a power. Here, this is 1 over x to the 1/2. And while we did have a quotient rule for derivatives, we don't really have, per se, a quotient rule for antiderivatives. So to make this not a quotient, we would do something that we've done before, and we would make that fraction go away by moving that to the numerator and making that exponent negative. So now everything we have uses the power rule, x to a power. So when we take our antiderivative, we do 1 more than 1/2. If we add 1 to 1/2, that's 1.5, or 3/2. So that's x to the 3/2 power over 3/2. And when we add 1 to negative 1/2, we get positive 1/2 over that power plus c. Or we could call this 2/3 x to the 3/2 plus 2x to the 1/2 plus c. If you want to, you could change back to radical notation, and we could call this 2/3 the square root of x cubed plus 2 square roots of x plus c. You could simplify this radical. Since we have 3 factors of x under a square root, we could pull one of those x's out, or pull 2 of them out as x and leave 1 x underneath. But that would be okay. So would that. Now we said we don't have a quotient rule. So what if we have something like this if we don't have a quotient rule? So we're going to have to use techniques like when we first did derivatives before we had a quotient rule for derivatives. We can take each term and divide it by the denominator. first term over the square root of x and the second term over the square root of x. So for the first term, we have x to the first on top, x to the 1/2 on bottom, and we can simplify that. Let's go ahead and write the second one as x to the 1/2. Remember, when we are dividing and our bases are the same, we subtract our exponents. The exponent on top minus the exponent on bottom, only if the bases are the same. So 1 minus 1/2 is 1/2. For the next term, we can leave the 2 on top. We don't want this to stay on bottom, so we could move it to the numerator as x to the negative 1/2. Now, if we integrate, you'll hear me interchange getting an antiderivative and integrate. Those are interchangeable. What we're finding is referred to as an indefinite integral. So we do x to the 1 bigger power. We said 1 more than 1/2 is 3/2 over 3/2, 4 times 2/3, plus 2 times x to the 1 bigger power, so 1 more than this is positive 1/2 over 1/2, 4 times another 2. And then we have our plus c. So that simplifies to 2/3 x to the 3/2. 2 times 2 is 4, x to the 1/2 plus c. Notice if we were to take the derivative, when we bring the 3/2 down, our coefficients would cancel. If we bring the 1/2 down here, 4 times 1/2 would be 2. And here, this doesn't have a coefficient, that has a coefficient of 2. So, yes, it looks like we went in the right direction there. We also had that the antiderivative of cosine is sine plus c, because the derivative of sine is cosine. The antiderivative of sine is negative cosine, because the derivative of cosine, if we take the derivative of cosine, we get negative sine. If we integrate both sides, essentially the integral and the derivative cancel, and we could multiply both sides by a negative, and that would become negative and that would become positive. So the integral of sine is minus cosine. So if we have an integral that involves a sine and a cosine, then we can, if we have terms, we can integrate those separately. So 3 times the antiderivative of sine, which is negative cosine, plus 7 times the antiderivative of cosine, which is sine, plus c. So minus 3 cosine plus 7 sine plus c. So any trig function, if we know the derivative of sine, cosine, tangent, secant, cosecant, cotangent, then if we take the antiderivative of what those came out to be, then we know where those came from. So let's do another one. And in this problem we're going to have 2 concepts. One of them is that if we have a second derivative, to get the first derivative, we integrate. And if we integrate a first derivative, it gives us our original function. So let's write that out. If we integrate a second derivative, it gives us the first derivative. And if we integrate a first derivative, it gives us our original function. Because we're doing an antiderivative, we're going backwards. If we take the derivative of a function, it gives us f prime. If we take the derivative of f prime, it gives us f double prime. So an integral goes the other way. It finds what function has this as its derivative. That's the first derivative. What function has this as its derivative? That's the original function. So they give us some initial conditions. They say that for our function, if we put a 2 in, we should get 19. And for our derivative, if we put a 2 in, we should get 13. Now, why do we need to know that? Well, if this is our second derivative, then when we do the antiderivative of that function, we have a constant, and when we integrate a constant, we pick up our variable, but we also pick up a plus c. And when we take the antiderivative of this, that's our first derivative. This data point, that's going to help us find c. So in our first derivative, when we put a 2 into our first derivative, we would get f times 2, or 4 times 2, plus c, and the answer when we plug 2 in should be 13. So 4 times 2 is 8. How do we get c by itself? Yeah, we subtract 8 from both sides. So this c is 5, which means that our first derivative, instead of having a general first derivative that has a plus c in it, our specific first derivative for our problem is 4x plus 5, not just 4x plus an arbitrary number. Once we know our first derivative, we can integrate it to get our original function. So if we take the antiderivative, 4 is a constant, a coefficient, x to the 1 bigger power over that power. 5 is by itself, so when we integrate a constant, we pick up our variable, and then we always put a plus c on the end. And this was our first derivative that we just integrated, and that the integral of a first derivative is our function. So 4 divided by 2 gives us 2x squared plus 5x plus c. And to get that c, we are given a value. When we plug a 2 into our function, plug a 2 everywhere we have an x, and as a reminder, anytime you plug into a formula, put a parenthesis around what you're plugging in. When we plug a 2 into our function, we should get 19. So 2 squared is 4 times 2. 5 times 2 is 10. 8 plus 10 is 18. So 18 plus what is 19? Well, 1. So that makes our function 2x squared plus 5x plus 1. So we started out with a second derivative, and we started out with a value, a point in the first derivative and a point on the original function, and we were able to come up with what f is. Now I want to walk through one more problem, and not really so much a specific problem, but let's talk about when we have constant acceleration. So when we take an object and we drop it, or even if we take that object and throw it up in the air, it undergoes an acceleration due to gravity. And if we're assuming that acceleration to be a constant, then we have this general equation, or we could call that K, or C. So let's make up an example. Let's suppose that our velocity when we start is 6 meters per second, and it's going up, and let's consider up to be positive. And our initial position is 30 meters. Now, acceleration of gravity is negative 9.8 meters per second squared. And for the most part, that's constant. Now, those of you that have taken physics before know that acceleration is affected by the distance between two masses. So as you get farther from the center of the Earth, then your acceleration does change. But it takes a pretty big change before we impact our acceleration much. So if our acceleration is a constant, remember that if, let's just call, if I used x here, let's actually change that to y. If we have our height as y, if we take the derivative of that, the derivative of position is velocity. That's how fast position is changing. And the derivative of velocity, how fast velocity is changing, is acceleration. So if we have acceleration, which is a constant, if we take the antiderivative, it'll give us velocity. The derivative of velocity is acceleration, so if we go backwards, we're taking the antiderivative. And our variable is time. So if we take the antiderivative of that, we get negative 9.8 t plus c. And we're told, so that's velocity. We're told that our velocity when t is 0, so if we put a 0 in for t, that initial velocity is 6 meters per second. Anything times 0 is 0, so c would be 6. So our velocity function is negative 9.8 t plus 6. Now, velocity is the derivative of position. So if we want position, we take the antiderivative of velocity. So if we integrate that, negative 9.8 is a constant. T to the 1 bigger power over that power plus 6 times, if we integrate a constant, we pick up a t plus c. Now, normally we would divide those out. I'm going to leave this as, I'm going to call it 1/2 times negative 9.8 times t squared plus 6t plus c. And we're told our initial height when time is 0 is 30. So our height is 30 if we put in a 0 for t. So if t is 0, that's 0, and that's 0. So this c, which is a different c, is 30. So y is, let's call it 30 plus 6t plus 1/2 times negative 9.8 t squared. And the reason I wrote it this way is because our general kinematic equation is initial position plus initial velocity times time plus 1/2 a t squared. Negative 9.8, that is our acceleration. So this whole kinematic equation for projectile motion actually comes from integrating acceleration and then integrating velocity to get position. In chapter 2, we started with this function, and we took the derivative of it to get velocity and the derivative of that to get acceleration. But it actually comes from starting with the fact that acceleration is a constant. When we integrate a constant, we pick up a variable plus c. That c stands for our initial velocity. And then when we integrate that, we pick up a t squared over 2 and another t. So that's where our kinematic equation came from.